In this tutorial, I will show you how to design a simple calculator and what are the basic steps required to complete a difficult problem. And I will do the code from the scratch and all the interfacing uh, in Proteus. So what is the problem? The problem over here is to design a simple 4-bit calculator that can perform arithmetic operations of two 4-bit numbers. So we have two 4-bit numbers, and the first 4-bit number will be coming from port 1 and second number through the remaining 4 bits of port 1. Okay, so I have to make a port 1 the input port. Input will be provided through single pole double through mechanical switches. So these switches are also available in Proteus. There will be 4 push buttons attached to port 0 through which user can enter the required mathematical operation. So from these are the mathematical operations. So if user press the button attached at 0.7 pin, then I have to perform the addition. Okay, after entering numbers to port 1 and selecting operation from port 0, user will be able to see the required result on port 2. So I have to show the result on port 2. So these are the basic requirements that I have to complete. So let's see how can we do its program. First I will create a project in Keel like Grooming. The microcontroller I'm choosing is of 8051 family series 89C52. Now I have to create the ASM file. And I will add it to my source group. Okay. It is not here. Why is it? Hmm. Okay, so it is over here. It has been added here. Second thing is to set up the hardware, because we will be doing the real-time testing of our code. I will save it in the same directory. Now I have to place the ports. Number 1 is 80, 89, C52 microcontroller. We need SPDT switches. And one, two, one more. So these switches will provide me the input at, where do we have the input? At port 1. Okay. Okay, now we have to provide two conditions. One will be the 5 volt and other one is going to be the ground. So power, okay, it is over here. This is for the 5 volts and this one is for the ground. We will common all of these second inputs to ground. And all the first terminals will be connected with the 5 volt. Okay, now if I just simply run it, let's see if we can send the two logics. So we can see it is turning red, it means the 5 volts are going there. Oops. And now the next part is to attach push buttons. Let's see if we have a push button. Yes, it is over here. And 0.4567 4 5 6 and 7. Okay, so now I have connected these push buttons with port 0.4 and if we test it with this one, as you can see the 5 volts are passing through this push button, but we haven't programmed it yet. So the last connections over here are these ones. User will be able to see the required result on port 2. So we have to connect port 2 with LEDs. It can be the 7 segment or simple LEDs. I will be connecting the LEDs. Okay, we click connect these LEDs and pause this video so that it does not get lengthy. So now our basic setup is ready. Switches are connected and LEDs are also connected. We will start the coding part now. So how are we going to solve it? Let me open the lab manual again. So here is the task. Now first I am going to read the data from the ports and split it and send some data on the LED board to see if it is working or not. My inputs are going on my outputs. Let's see how I'm going to do this. Port 1 is so I'm sending ones on port 1 to make it an input. Zero. We are reading the operation from port 0. And it is going to be 0 hex there. You can skip this part as well because we don't have to define an output port, but I'm doing it anyway. Let's read some data from port 1 and send it to port 2. I'm using an intermediate variable. We can also send it directly over to port 2. We have to do some settings over here. Change the crystal frequency according to 8051 architecture and create the hex file. Let's compile it and see if there are any errors over here. So there is no error. I will include the hex file over here and have to change this frequency 11.0. So this is the hex file. Okay, let's see what happens now. So this one is going there. So these switches are working perfectly. My data is going to the port. Now what I have to do, I have to split it. First 4 bits of the port 1 is the first number and the second 4 bits are the second number. Okay, so we have got the number in A. We will have 0, let's do the masking. Okay, for masking what I can do and I will save the data in R0 and hash 0 masking upper nibble. Okay, so upper nibble. I hope it has been masked. So let's test it if working on it. Pause it and play. So we can see that only 4 bits can pass over there and remaining bits have been lost. So this is going to be our first 4 bits is our first 4 bits will be used for the first number. The first number, so let's move it to another register or 0, comma a. So first 4-bit number. Well, here is a mistake. If I'm going to send the data simultaneously or concurrently, so if I do the masking over here, I'm losing the remaining data. So let me save this data. Let's say in B, save copy of data. Now I can reuse it. Move, comma, B, and then because I want the lower nibble as well. Lower nibble as well. No, I already got the lower nibble. I want the upper nibble. So for upper nibble, what I can do is I will do another operation, and this time I'm going to mask the masking lower nibble. So lower nibble has been masked. So let's see what happens. I can only test the lower nibble, upper nibble now. So this data is going there, and the lower nibble has been masked. So perfect. So we are making some progress. So I've got the two numbers, and I have to perform the addition, subtraction, and multiplication. Before doing this, I have to move this upper nibble part to the lower nibble, just like this. Let me explain it in a better way. So currently I have one. Let's say this is the upper nibble, and the lower nibble is masked, so it will always remain 0. But when I have to perform the mathematical operation, I need this data over here. So we can simply rotate this data. Rotate left or rotate right? Rotate right. Then again. Then again. So 4 times I'm going to rotate it. And let's see what happens now. I should see the data on the lower nibble now. Okay, so after rotating the data, we can see that we can see our data on the lower nibble, which is 0.0. I thought I was doing it wrong, but it is perfectly fine. First, the data was shown over here, but after rotating right, it can be seen over here. Now I have got both the nibbles, as I've explained that for arithmetic operation we need both nibbles in the same lower part. So this is the upper nibble. What I did, I used the rotate right command, and it sent each data to the next bit. This one will move over here. So this is what rotate right does. So this is so far this is what we have achieved. So what is the next part? I've got the data. Now I need, if it is I have to check if it is addition, subtraction or multiplication I have to perform. For that I have got the data. I have to check now. There are multiple ways to make this condition. We can use J and B or JB. Any of this condition will be fine for us. And we can also use CJNE. So let's see what we can do. If I use J and B, let's use JB. P 0.7, comma, addition. I hope I'm not writing the wrong syntax. Subtraction. So let's compare it. Okay, so this is the wrong symbol. Let me check the syntax as well. So there is simple one. It is, I haven't told where it should jump. Addition, subtraction. Well, it will show error over here as well. Okay, let's comment this one for a second. Okay, now the syntax is correct. So now when I'm going to get the signal at 0.7, I should perform addition. So I have defined this label addition, and we can simply call a function over here. A call, let's change the name AD. So this function is going to perform addition for us. Addition, and move A comma R0. We need data in these registers for addition, I guess so. R1, and I'm also going to delete whatever is present in A or B, so it does not ruin our data. So I've cleared A and B, moved the saved data in R0 and R1. And let's perform the addition. So add R0, sorry, A comma B. Add them, and I guess we have to send the data as well. So to send the data, move P2 comma A and return. So we will remove this one now. So if JB.0.7 is pressed, we should perform addition. It will jump over here, it will call the addition subroutine, and it will perform addition. And if it is not 0.1, it will come
all the way over here, so we will jump. Yes, jump. Skip. So skip is basically we're going to be skipping this subroutine, and it will come all the way over here because we do not want to call addition if point 7 is not pressed. So let's see if it works or not. Okay. This is 1 and this is going to be 1. I hope it works. So 1 plus 1 is 2. Okay, let's change it to 3 plus 3. So 3 plus 3 is going to be 6. Let's perform addition as well. Again, okay. So this is 6. And what else we can do? So addition is working perfectly. This is good. That what else? 4 plus 1, so it is 5. So I have completed this addition code, and I will do the remaining code now over here.
And now we have to perform subtraction, multiplication and division. Addition part is working perfectly. We have seen that if we divide this problem in small steps and keep testing our code in real time, we can quickly troubleshoot it if there is any error, and we can come to the conclusion that we can solve any problem if we divide it in small steps. So the second part we have to do is subtraction. So for subtraction we will check 0.6, and if it is subtraction we should jump to the subtraction label. So this is the subtraction label. Okay, now in subtraction it is going to what it is doing. Okay, take all, let's name it sub I. So if it is subtraction, it should, if 0.6 has been pressed, we should jump to this label and call the sub I subroutine. Now we will define the subtraction subroutine, and it is really simple. Just name it, change the command, and it will perform the subtraction. A few things you should always note that 8051 always execute the code in sequence, and that is why I wrote sjump skip. So when we read data over here in P0.7, if it is 1, we will go and go to the addition label. But you can notice over here that when we will perform the addition, we will come back, we will go in this addition subroutine, perform the addition, and we will come back over here. And it is also going to perform the subtraction because it is not skipping, it is the code is executing in sequence. So I'm just going to add skip. So it should skip this as well, and here we go. Now it should work perfectly. It is going to skip it, and it will start again from here, and it will not mess up our code. Otherwise, if we are not going to add the skip as jump skip, it will perform the addition and it will also perform the subtraction. So this is what we do not want over here. So let's see if our code works or not. Okay, let me run it again. So I've set 1 and 1 over here. Let's perform addition. So 1 plus 1 is 2. Let's subtract it. So 1 minus 1 is 0. and 3 plus 1, or maybe 3 plus 3. We know it is 6. So the LOD's order is reversed. I should have put it this 2.0 over here. So you should know that this one is LSB the way I have connected. So it is 6, and if we minus 3 out of 3, it should be 0. And let's add 3 plus 2, it is 5, and if we subtract it, it is 1. So this is working perfectly again. Let's move toward the next step. The next step is, what was that? Multiplication. So for multiplication, we are checking 0.5. Let's write mult as a name, and I'm going to do the last part as well. Let's name it db, and we will go to their respective labels. Now I have to write assumptions. So when we return from subtraction, we don't mess it up. Okay, mult, and another label we need is db. So in mult we will call, let's name it multi subroutine, and then when we are going to execute the multi subroutine, we should skip the next immediate next code, that is of division. We call, we have to name it differently, dv, maybe this. Okay, we don't have to write sjump skip because we do not have any other code down there. It will automatically go to sjump main. So let's make some changes over here. Okay, what was the name of the function? It is multi. Let's place multi over here. And for multiplication, change the syntax and the result. And for this, change the name, change the syntax, and send the result. I hope I have done it correctly. So let's test it. So what do we have over here? Let's simply test 2 multiplied by 1. So 2 multiplied by 1 is not working, I guess. No, okay, 3 multiplied by 1 is 3. And 3 divided by 1, it should be 3 as well. 3 plus 1 should be 4. 3 minus 1 should be 2. So I think we have completed this code. Okay, so what else do we have over here? Okay, it is completed. So this is the way to do the programming in 8051, and I hope you have learned something from it. You will rectify the mistake you usually made in your codes. So in a nutshell, 8051 can only be learned if you start performing it, start doing the coding, and if you're not doing it, then you won't be able to learn it. And always divide the difficult task into small steps and test it if it is working or not on Proteus. So thank you. Goodbye.